All right, so this is our mathematical conversions. It's topic 1 of the physics unit. So this is just looking at sort of how we sort of change numbers and convert them when we're dealing with physics. And you may have learned about some of this in science or in math before. So we're going to first go over scientific notation. And I've already looked at this and realized that this slide has a huge mistake. They've mixed up right and left. So I'm just gonna fix that so it won't mess us up. All right, so scientific notation, this is basically used to make, or I guess short form, write a number that is either really large or really small. That's how we normally use scientific notation. So 127 here, we likely wouldn't normally use scientific notation. It's not a really big or really small number, but it's a good one to use to show you how we do scientific notation. So at the very top here, I've wrote down that the big thing about scientific notation is that the number must be between 1 and 9.9. So I say 9.9, 9.999, whatever numbers are past that decimal, but it can't be 10. 10 is too high. We only want to have one digit there, okay? So what that all means is basically, if we take this 127 here, we want to make it 1.27. So we're putting a decimal to make it a number that's between 1 and 10, or 9.999, all right? And then we're going to write times 10. And we write a times 10 to the something. We need to write an exponent there. And our exponent is going to be the number of places that we've moved our decimal. And you might look at 127 and say there's no decimal. Well, if there's no decimal, we assume it's at the end. Because if it was like this, 127.0, that's literally still 127. Okay, so we start there and we want to move our decimal to where it is at 1.27, and we're going to count the spaces that it's moved. So I always do this little visual way, 1, 2. So it's between the 1 and the 2 there, it's moved 2 spots to the left, okay? So we're going to take this and we're going to write a 2 up here. Now, I'm just going to read the bottom here because that is going to sort of help us to figure out whether it's positive or negative. It says a positive exponent indicates how many places the decimal moves to the left. For us, like I said, we have moved to the left. So by moving it to the left, we have a positive number. So this is correct. If we're moving our decimal to the right, then we are going to make it a negative. And you're likely going to see that in the next question. So let's try out the next one. We want to make this number between 1 and 9.999. So I'm going to move this decimal. 1, 2. And by moving it there, it's going to be 9.07. Okay. Not sure why that's not really working. So 9.07 times 10. We need times 10 to the what? Well, again, we've moved it 2 spots, right? We went 1, 2. So we're going to put a 2 there. Sorry. Wow. I think I skipped to the end. So we're going to put a 2 right there. And because we've moved our decimal to the right, like what we see right here, we're going to have to put a negative. So this is going to be negative. I can't. Wow, this pencil is not the greatest. Negative 2. So it should be 9.07 times 10 to the negative 2. So that's literally the same thing as 0.0907. All right, just a different way of writing it. Sometimes people will see those numbers and get like scared. Don't be scared. You can put it into your calculator. We've given you calculators that you can do this on. I don't have those calculators handy, the ones that I got from Mr. Naylor. I sent them in your guys' package, but you should be able to put it in there using like an exponent button or something. I can post maybe how to do that for that specific calculator on the Google Classroom. So here's some ones to practice. Convert each of the following from decimal notation to scientific. I'll do these ones out with you. Or for you, I guess, since I can't see if you're doing them or not. So this first number, 2,500, we don't have any decimal. So when we don't have a decimal in the number, we assume it's at the end. We move it 1, 2, 3 to make that number 2.5. And because we moved it 3, we put a number 3 at the top. Remember, it's moving to the left. It's a big number, so it's not negative. Think of small numbers. We put the negatives. Second one here, our decimal is right here. We want to move it 1, 2, so that becomes 1.8903. We've moved it 2, so it's a big number, and we've moved it to the left, so it's a positive. Our third one here, 0.025, that's a small number. We're going to have to move our decimal to the right, which means our exponent's going to be negative. 1, 2, it would become 2.5 times 10 to the negative 2. Okay, and then the last one here is 0.00307. We are going to be moving it to the right. It's a small number, which means our exponent will be negative. To get it to be 3.07, so 1, 2, 3. Okay, so that's some examples there for you. If you're having any trouble with those, let me know, and we can work to figure it out. Now they're going the opposite way. So they're saying convert each of the following from scientific to decimal notation. To do that, it's a little bit more tricky maybe in your mind, but it's not that bad. So how I always do this is, well, it's 2.3. I'm just going to write 2.3 here. Now, our next step here is to look at our exponent. Whoa, that's really big. All right, so our exponent is -4, which means that it's going to become a decimal, like a smaller number, and we're going to be moving that decimal to go backwards. We're going to be moving it left. So I'm going to put 4 zeros here, and I maybe didn't leave enough room. So I go 2.3, and then I'm going to put some zeros here. All right. Now I'm going to move my decimal backwards. So 1, 2, 3, 4. So the number would be 0.00023. Okay, so that's how I do it to get to that answer. Let's try another one. It's a little bit harder to see. What's something to really note here is that, you know, how normally we were moving the decimal to the left would be a big number. Well, we're going backwards, so it's the opposite. So negative exponents will be moving it to the left. Positive exponents will be moving it to the right to get our decimal notation. Okay, maybe I can write that up here. So positive exponents and negative. So positive exponents, we're going to be moving our decimal to the right. And negative, we're going to be moving it to the left. All right, the second one here, 5.0 times 10 to the 3. So again, I'm just like to write out the number. It's going to be a larger number because it's a positive exponent. So I'm going to add 3 zeros there. So the exponent is sort of telling you where you're going to add the zeros. For a positive number, we're going to be adding zeros to the right-hand side. For a negative exponent, we're going to be writing zeros to the left-hand side of that number that we have. Now I'm going to move my decimal 3 spots. 1, 2, 3. So my answer here is going to be 5000 decimal 0 if you would like to write that, but it's really just 5,000. Our next one here, 9.25. And it's times 10 to the 1. So I'm going to write an extra 0 over here. We're only going to move the decimal 1 place that way. So our answer is going to be 92.50. All right. And then our final one here, 1.8. We have, it's a negative, so I'm going to add 2 zeros there and then move my decimal 2 spots to the left. 1, 2. So our final answer is 0.018. All right. So that's exactly how you are to do this scientific notation. You should have learned about this in math at some point up until now. And something to really note is that if you really don't know how to do it, if you put like 1.8 times 10 to the negative 2 in your calculator, it'll tell you this decimal answer. Just press equals and it'll tell you, which is pretty cool. So you have that sort of tool at your disposal. So when we're talking about units, it says when converting a value from one unit to another, it's often helpful to use the unit analysis method. So the unit analysis method is basically sort of, I call it a conversion factor. That's what I've learned. It's what you use to convert from a certain unit to another. And it's normally a fraction that you're going to multiply this number by. So it's giving you this example, and I'm going to show you how to do this. So this is something that you're going to use from now on, and if you do any more physics, so even in Science 20 and 30, we use these conversions, and we'll go over them again, but it's always helpful to understand them now because this is going to help you as we go through this section. So it says convert 25 kilometers per hour to meters per second. So how I do this is I times it by, notice how I put the kilometers divided by hours to really write it like that because it helps you to see how we're going to do this. And I'll get to, I guess, what that means as we go through this. But the 25 is on the top, and kilometers is on the top, and it's H's, or the hours, are on the bottom. What we want to do here is we want to change it into meters and seconds. And I'm going to do this in 2 conversion factors or unit analysis steps. So the first step is we want to get rid of hours and kilometers. I'm going to get rid of hours first. I'm not sure why. But to get rid of something when you're dealing with fractions is if we have hours on the bottom, if we put hours on the top, I'm going to write 1 hour, then hours will cancel out because it's almost saying like hours divided by hours. Well, if you divide anything by itself, you're going to get rid of it. It's just going to be 1. So that's how we get rid of the hours. Our conversion factor here is telling us how many seconds, because our hours are going to be changed to seconds. So we need to write on the bottom how many seconds are in 1 hour. And this is something that you will likely just need to remember. It's 3,600. This is a very common one that you're going to be using. So remember that there's 3,600 seconds in an hour. All right. So now we've got the unit that we need. Maybe I should use blue. Now we've got seconds on the bottom, which is what we want. We want seconds on the bottom. Perfect. Now we want to get rid of kilometers. And you notice how kilometers is on the top? So to get rid of it, we need to write it on the bottom. I'm writing 1 there because we're saying in 1 kilometer, there's how many meters? And the answer is 1,000. So 1,000 meters is 1 kilometer. So we write that there. Something that to note here is that we've got rid of kilometers. Kilometers was on the top and now it's on the bottom, so we've got rid of it. So what we're left with here is meters over seconds. So how we do this calculation is we just need to multiply across the top and divide by whatever's on the bottom. This is really not working very well. All right, so it equals. So on my calculator, what I'm going to do is I'm going to take 25 multiplied by 1, because we've got a 1 there, 1 hour, and then multiplied by 1,000. So by doing that, I get 25,000. And the only thing that's not out is meters. All right, so we still got meters. Divided by, the only 2 numbers on the bottom are 3,600 multiplied by 1. So we're just multiplying across the top and across the bottom. And that is seconds. So now what we can do is we can divide these 2 numbers. So we take 25,000 divided by 3,600. And we will get 6.94 repeating. And that is meters over seconds. Okay? So if we are driving in our car, we often will use kilometers an hour. It says it right on the speedometer on your car. It's going to tell you how fast you're going. And I mean, in Canada, we use kilometers per hour. If you're in the States, then they'll use miles per hour. But we won't have any questions that deal with that. But it's something to note if you are driving there, sort of knowing that conversion. But in general, when we're driving, we use kilometers an hour. And then when we are talking about physics, most things will use meters per second. So that's why we've got to know this conversion and know how to convert from one to the other. All right. There's some practice problems here. I'm going to do one of them for you. I'll do B just because that's going backwards. I'm not going to do all of these ones, but you're more than welcome to, and I can tell you maybe the answer or if you have any trouble with them. So let's do B. I'll do it in this space right here. So we want to convert 1.2 meters over seconds into kilometers an hour. So this is literally the same thing. We're just going the opposite way. If we want meters on the top, we want meters on the bottom. Our meters is going to change to kilometers. In 1 kilometer, there's 1,000 meters. And then our seconds is on the bottom, so we want seconds on the top, and what we want on the bottom is hours. In 1 hour, there's 3,600 seconds. All right, so again, we just multiply across the top and the bottom. What I like to do here is go 1.2 multiplied by 1 multiplied by 3,600 gives me 4,320. And sorry, I didn't cross out the seconds. What we're left with there is kilometers, which is important. And then our hours should be on the bottom, and then it's just 1,000 times 1, which is 1,000. So our answer here, if we divide those two, will give us 4.32 kilometers per hour. All right. So it's exactly the same. We're just setting it up, and there's some people will say like, oh, whenever you're converting from this to this, you times by 1,000, divide by 3,600 or whatever it is. And to me, like, that is confusing. I'm such a visual learner that I need to be able to just write it out. You don't need to remember. You just got to figure out, well, if I have meters on the top, then I must need to put meters on the bottom. And if I have seconds on the bottom, I need to put it on the top so that they cancel out. And by doing that, you create the problem that other people have just remembered in their head. But I don't like to remember things per se. I like to remember how to do them. And if we know the process, then we don't have to keep as much things in our brain. At least that's my opinion on that. All right, so that is how you calculate that. You changing from meters per second to kilometers an hour. Now we're going to go over significant digits. So it says in science we can describe a given value, as having a defined number of significant digits, or digits that matter with regards to accuracy. So the use of significant digits allows for a higher level of certainty when reporting a final value. The number of sig figs or sig digs that are final value is recorded to depends on how many digits were recorded in the initial value measured. Rules must be followed for different operations to ensure that if the initial values are mathematically manipulated, final values are reported to the same level of certainty. So it says 9,000, this little meme, has one significant figure while 12 has two. Okay. So let's just go over some of the rules of significant digits. Sometimes people will call it significant figures. That's what I was taught. So I call it sig figs. This calls it sig digs. Whatever you want to call it. So it says all digits from 1 to 9 are always considered significant. So if we have the number 1.23, then all of those digits are significant. Zeros placed between two non-zero digits are always significant as well. So if we have 1003, all of them are significant, even though they're zeros, because they're like sandwiched in between. And I like to write. Oops. To remember that sandwich zeros are significant. These are 1 to 9 is significant. Zeros to the left of non-zeros digits are not significant, so no zeros to left. Rules for determining significant digits. Again, number 4 is any zero to the right of a non-zero digit is significant if it is also to the right of a decimal. So any of the digits, so we put 2.0, those are two significant digits, as well as 0.020. Because that 0 is written there, Why would you write it? If they write it, it must be significant. So, so zeros right of a decimal number are significant. And then the last one here, any zero to the right of a non-zero digit that lacks a decimal is not significant. So 10 or 10,000, they both just have one significant digit. So in general, these ones just zeros. That are right of a number that's between 1 and 9, those are not significant. So that's a lot of rules here. Let's try these out. So it says practice, determine the number of significant digits in each of the following. So remember, the very first rule is that every number that's not a zero is significant. So in this one, we have no zeros. It's got to be 3. 2 significant, 8 significant, and 3. Again, there's no zeros in this one, so it must be 4. Really, it's all the numbers that are there that are not zeros will always be significant. So the only rules that you have to remember is where the zeros are and whether they're significant. This one, 1 is significant, and 4, obviously, they're not zeros. And then there's this decimal 0. So one of the rules here was that if a 0 is after a decimal, then it's significant. Here, on the other hand, we've got 0.003. One of the other rules was that zeros that are just before a number right after a decimal, those are not significant. So we would only have 1 here. Same with this one. So these two not significant. 4 is significant, and then because they've put that 0 there, why would they? If they did it, it must be significant. Okay. When we're doing scientific notation, when you're reading these decimals, you're only looking at the digits. You're only looking at the numbers there. This part does not matter. Okay, so we're only looking at 5, 4, 4. None of those are zeros, so they're all significant. 4,500, we know 4 and 5 is significant. These zeros, because they're trailing, they don't have any decimal there, they are not significant. And then finally, this one, this is my favorite type, is that the zeros that are sandwiched, it's the sandwich one, those are significant. So because this 0 is between non-zeros, it becomes significant. So why do we use significant digits? Well, basically it has to do with accuracy. You can't be more accurate or more precise than the numbers that you started with. That really doesn't make sense. So adding a value that is much smaller than the last significant digit of another value is often irrelevant. When adding or subtracting the number of significant digits is therefore determined by the value whose sig digs is furthest to the left when numbers are aligned according to the decimal place. I don't understand what this means. So if we're adding 13.64, this has 4 significant digits, this one has 2, and this one has 2. I'm not exactly sure what they mean by lining them up, but if we're adding 3 numbers together, our answer can only be to the lowest amount of significant digits in the question. So our lowest amount is 2. So our answer can only be to 2. We can't put like 81.064 or whatever it is, because we can't be more precise than where we started. So we're like as strong as our weakest link, and our weakest link is the one that has the lowest amount of significant digits. All right. So if we practice this, you're literally just going to use your calculator to do this, but so I'm going to do that. I'm going to go 83.25 minus 0.1075, and my answer is 83.1425. So this answer has 1, 2, 3, 4, 5, 6 significant digits. Way too many. Where our question, we have to analyze the question. This one has 4, and this one has 4, which means our answer can only be to 4. So basically what that means is we're going to round the number. It would be 83.14. So the reason why this 4 stays as a 4 is because this number 2, in order to round that number up to be like 83.15, this 2 would have to be a 5 or higher. And because it's not, we just cut that 5 off. Okay, so our answer is 83.14. Our next one here, 4.02, that has 3 significant digits, because this is sandwiched. And then this one, because these are ones that are placeholders, they call them, there's really only 1 significant digit in that question, because it's only the 1. So if we go 4.02 plus 0.001, our answer is going to be 4.021. So that's way too many digits. We need to round it to 1 significant digit. And the 1 significant digit is just going to be 4, because this number is not higher than 5. So we're going to keep it at 4. So that would be our answer. Okay. So really adding that 0.001 literally did nothing. And that's what it said over here, is that sometimes when you add a small number, it's really irrelevant. It's not going to be helping in any way. The last one here, 0.2983, that has 4 significant digits, and this one has 3. So our answer has to be rounded to 3 significant digits. Right there, it's got 5, so we need to round it to 3. So basically we write 1.8, if I can write. And if we put it as 1, that would be wrong, because the next number is 8. So that's higher than 5. So this becomes 1.82. So I hope that makes sense, that we need to round that number up, because this number is almost to 2. It's like 1.83, closer to 2, so we would round that number up to 2. Okay, so our final answer is 1.82 with 3 significant digits. Okay, so again, what we're doing here, analyze your question, find the part of the question that has the least amount of significant digits, do the question, and then round your answer to the amount of significant digits that exists. How we multiply and divide with them, it's literally the same thing as far as I know. We're just counting the significant digits in the question. So we can try these ones out again. So let's look at our question. 7.255, that's 4 significant digits. 100 is only 1, because these zeros, there's no decimal there, so they don't count. So we're left with 1. So if I do this out, 7.255 multiplied by 100, that gives me 725.5. I don't like this. 725.5. and we want to round that to one significant digit. So to do that, this number is 725, if you really look at it. So we're only going to be able to have one number. So it's either going to be a 7 or an 8. So is that closer to 700 or is it closer to 800? Well, it's really closer to 700. So we're going to round that down to 700. That way there's only one significant digit. All right. Next one, this question, because this decimal's there and this would actually have 4. And this one would have 3 because it's sandwiched the 0 between the 2 and the 5. So our answer would have to have 3. So we're doing 120 divided by 0.0205. And my answer gives me 5853.65854. Probably didn't need to write all those decimal places because we're going to be rounding this to 3 digits. So we got 585, and then it's 3 after that. So because this 3 is not higher than 5, we're just going to write it like that. The final one here, this one has 3 significant digits and this one has 4. So our answer will be 1.04 multiplied by 225.0 gives us 234. Is that right? Yep. And that answer is to 3 significant digits, so it's set. We don't need to do any rounding. Every piece of equipment designed to measure specific quantities has an error associated with its precision. For example, some apparatuses here, we've got a balance or a scale. There's some uncertainty. It could be 0.01 grams off. A thermometer could be about half a degree off. A graduated cylinder could be about 0.2 to 1 milliliter off. So basically it's telling us we can only be as precise as the instruments that we use. The number of decimal places you round your measurements to must be the same as the number of decimal places in the uncertainty. So for example, our scales will have an uncertainty of plus or minus 0.01. So when recording the mass of a substance, you should record it to 2 decimal places. Because we've got 2 decimal places, we've got 0.01. That's showing us that we can go to 2 decimal places. For analog equipment, like a ruler, so analog means it's not digital in any way, the uncertainty is plus or minus a half of the smallest scale division. So for example, on a ruler, the smallest scale division is 0.1 of a centimeter or 1 millimeter. So therefore the uncertainty is plus or minus 0.05, so half of that. And you can record your answers to 2 decimal places. So what about the second ruler here? What's our smallest measurement? Well, our smallest measurement here is 1 centimeter. So we can do our uncertainty to half of that. So it would be half of a centimeter. So that would mean that we could only do it to 1 decimal place. Okay. Sometimes it's more convenient to express the value in different units. When units change, the number of significant digits does not change. So if we have 1.23 meters and we want it to go into centimeters, it's still going to have 3 significant digits. This one in millimeters is still going to have 3, and this is still going to have 3 if we're putting it in kilometers. So just know that if we're converting units, we still are going to keep the same amount of significant digits. Okay, so that's a sort of overview of significant digits. And that is it. That's really all I have to go over with you today. So keep this stuff in mind as you continue through the physics unit. All right, and let me know if you have any questions, then I can help you out.